So one very important type of density curve is the normal distribution or the normal curve, right? The normal distribution is symmetric. It's a bell shape. Some people call it a bell curve. It has a single peak. And because it's symmetric, that single peak is our mean, is our median, is our mode, right? And much like a density curve, the entire area under our curve is 1, and that median divides our data set in half, right? So the area on the left-hand side would be 0.50. The area on the right-hand side would be like 0.50. And any normal curve is completely described by giving its mean and its standard deviation. So sometimes you'll see this notation where it's like n parentheses mean and then my standard deviation, right? This tells me I've got a normal distribution with this mean and this standard deviation. So one quick question is, are both of these graphs normal? The answer is actually yes, right? They both are symmetric. They both have one peak, right? That's important. The area under both curves is 1, I promise. It just happens that one has a larger standard deviation than the other, right? When you've got a wider standard deviation, your data is more spread out. And when you have a smaller standard deviation, it's more condensed towards the mean, right? So that area is less concentrated about the mean if I've got a larger standard deviation. So one rule I really like, and this is our great way to get a real good like gut instinct about normal distributions, is the 68, 95, 99.7 rule. And I did include a worksheet of this in our Canvas course with a key if you want to do some extra work. To make sure you've got a really good feeling and know how to use the 68, 95, 99.7 rule. So it says this. It says that we've got 68% of data within one standard deviation of the mean. So here's my mean. And if I go one standard deviation below and one standard deviation above, I'm going to have 68% of our data. If I go about 2 standard deviations above and below the mean, maybe green wasn't the best choice, right? I'm going to have 95% of data within 2 standard deviations. And then within 3 standard deviations above and below the mean, I'm going to have 99.7% of data, like under this curve, right? That area we could say it's like 0.997, right? We want to be good at converting between percentages and decimals / proportions, right? So most of our data is within 3 standard deviations, and that makes sense because anything greater than 3 standard deviations really should feel like gut instinct at this point, like an outlier, right? And outliers can kind of skew with our data. So here it is restated again, right? We've got 68% of data within 1 standard deviation, 95 within 2, and 99.7% of the data within 3 standard deviations of the mean. It's so important. I basically showed you the same slide twice. So let's work through a couple examples when we do have some things that are perfectly whole number of standard deviations above or below the mean. So the tests that make up the verbal, critical reading, and mathematics SAT are designed so that their scores are normally distributed with a, why did I make that sound? With a mean of 500 and a standard deviation of 100, right? So maybe I should have put mu sigma, sorry about that. And we could write this as the normal distribution with mean of 500 and standard deviation of 100, right? If we wanted to use that notation. So the first thing I want us to do is sketch the distribution and then interpret this by using percentages and the 68, 95, 99.7 rule. So I'm going to draw a normal distribution. Now it's not going to be pretty, right? But it is normal-ish, right? I know my mean's in the center, that's 500. And I want to go 3 standard deviations above and 3 standard deviations, below the mean. So my standard deviation is 100. So if I go 1 standard deviation above our mean, that's going to put me at 600. 2 standard deviations, that puts me at 700. 3 standard deviations puts me at 800. And then I can go the other way as well. So I've got 400, 300, and 200. So see, when I was adding standard deviations, what I was doing was adding 100 every time because I'm going up. And then when I was going below, I was subtracting 100 every time. So let's interpret this normal distribution using the 68, 95, 99.7 rule. So first, I have that 68% of SAT scores are between, this is me trying to write really nicely, I'll slow down, between 400 and 600 points, right? Our 68% of data was within this first standard deviation. Next, I have that 95% of SAT scores are between, right? Have you seen that parentheses to like repeat stuff, right? Of SAT, I'll just write it out. Scores are between, well, that's going to be 700 and 300. So this right here, that's 95% of my data. Next, I have that 99.7%, so almost 100% of our data, right, is within 200 and 300 points. So 99.7% of SAT scores are between 200 and 800 points. So this is great, right? This is great as long as I have data values that are a perfect standard deviation away from my mean. But my big question would be, well, what if I got a score of 662? What percentile would I be? What's the area to the left of 662? Like how many standard deviations is that away from the mean? And so for that, we're going to have to use something new, which will be the next video. Just kidding. I had one more example. Sorry about that. So in this second example of using the 68, 95, 99.7 rule, vending machines can be adjusted to reject coins above or below certain weights, right? That's trying to avoid counterfeit coins or coins that maybe are from another country. So the weight of legal US quarters have a normal distribution with a mean of 5.67 grams and a standard deviation of 0.07 grams, right? So I could write this as the normal distribution, that's 5.67.07, right? That's my standard notation. So if a vending machine is adjusted to reject quarters that weigh more than 5.81 grams and less than 5.53 grams, what percentage of legal quarters will be rejected by the machine? So the first thing I want to do is I want to sketch a normal distribution, right? When approaching problems like this, even future problems that don't use the 68, 95, 99.7 rule, I would always recommend sketching a normal distribution. Even if you just label the mean and whatever data value you're looking at, right? This is a great way to set yourself up for success when solving these types of problems, okay? So I need to go 1, 2, and 3 standard deviations above the mean, and 1, 2, 3 standard deviations below the mean, right? We don't need to go much further than that because remember, 99.7% of data is within those first 3 standard deviations. So if I go up 1 standard deviation, I'm adding, oh, that was strange, 0.07. See if I can erase that. Interesting. So I'm adding 0.07, so that puts me at 5.74, then I do that again, I'm at 5.81, 5.88. Next, I go below, so I'm at 5.6, 5.53, and 5.46. So I want to know if I'm rejecting quarters that weigh above 5.83, 5.81 grams, right? So that's, I'm rejecting, let's color it in. I'm rejecting up here, but then I'm also rejecting those less than 5.53. Now I know that that is the two standard deviations below and above the mean. So I know that 95% of data is between those two. So how much is left over? Well, I need to remember that the entire area under a normal curve is 1, right? This area would be 0.95. So if I want to find out what's left over, I could take 1 minus 0.95 to get 0.05, which is 5%, right? Or I could have taken 100% minus 95% to see that 5% of quarters would be rejected by the machine. So next, like I had mentioned at the end of example 1, we're going to figure out what to do if we aren't a perfect, whole number of standard deviations above or below the mean.